Okay guys, we're going to look at chapter 4.6, the moment of a couple. And as I tell everyone, this is not a moment between you and your significant other. This is not a moment that you have. That's another field of study. This is physics and mechanics. Okay, we're dealing with forces here, and the rotational effects of forces. Okay, first thing we need to look at is what is a couple. A few points, very important. A couple is essentially two forces, okay, of equal magnitude. That's very important. So let's even draw it here. The textbook goes minus F and F. This is that. Okay, so it's two forces equal in magnitude, opposite in direction, equal in magnitude, opposite in direction, and separated by perpendicular distance d. Okay? There's a distance d that's separated. Okay, so they're opposite in direction, which means they're parallel. Okay, but they have the opposite direction, they have the same magnitude, and they have the separation d. Okay? Based on this is a couple, okay? So don't get confused between a moment of a couple and a couple. A couple is simply the two forces, okay? A moment is the effect, the rotational effect that these two forces cause. Okay? So a moment is the rotational effect caused by the two forces, but a couple is simply defined by these three things. Now, the next thing I want to mention is that a couple produces pure rotation. Okay, pure rotation. What do we mean by this? It means that these two forces, right? If we've got a body here and there's F, there's these two forces. These two forces do not cause the body to move in that direction. It causes the body to purely rotate. These two forces only cause a rotation of the body. Okay? So there's no translation or no tendency for translation, meaning the straight line movement, right? Because can you see we've got these forces acting in this direction. So our thought would be that surely there, even though it wants to cause it to rotate, there might also be a tendency for it to move in up or down, right? Along the lines of action of these forces. But because they have the same magnitude and opposite in direction, the sum of the forces in this direction cancel out and become zero. So that force is cancelled out by that force. Does that make sense, guys? That force is cancelled out by that force. The sum of the forces in this direction are zero, meaning there's no translation. But because there's this perpendicular distance, it wants to cause a rotation. So that's why there's a couple causes pure rotation, no translation. Okay? Please understand that. That is quite important. Okay? The next thing which I want to discuss is based on, in the textbook, based on figure 426. Okay? Figure 426. If we have a body, okay, and we have these two forces, say F, let's use this, let's say, trying to copy the textbook as much as I can here, F and minus F. So what do we know? They're opposite in direction, they're parallel, okay? They're separated by a perpendicular distance, okay? What if we take moments about a point O? Let's take moments about a point O. Remember what we did before. In the previous chapters, we have simply we've got two forces and we want to find what is the resultant moment. Well, if we wanted to find what is the resultant moment about O, what would we do? We would say it's the sum of R cross F, where R is simply a position vector from the point of rotation to any point along the line of action of each of the forces, right? Okay? So, based on what the textbook does, here's the line of action of F, okay? The textbook chooses a point B, and then there is a position vector RB. Okay? So the position vector RB is from the point O to a point along the line of action of B. Okay? And then the textbook also chooses a point A on the line of action of this minus F vector. Okay? And then you would have your RA. Okay? So what do we have? We've got the moment due to this force will be RB cross F plus the moment due to this force, which is RA, because it's the position vector RA, it's this position vector there, cross minus F. And if we do some rearranging, we will have that the resultant moment about O equals RB minus RA cross F. Okay? That's what we're having. Okay, very straightforward. All we're doing was we've got two forces and we're taking the moments about a point. Okay, we've done it a million times. There's nothing new there. But what if we see from point A, okay, my drawing is quite horrific, so go and look in the textbook. What if we determine a position vector from point A to point B, okay, which essentially is what? It is a position vector, guys, from a point on the line of action of this force directed towards a point along the line of action of the other force. I'm going to repeat that. What is this position vector? It's a position vector from a point on the line of action of this force to a point on the line of action of that force. So if this becomes R, then what we have is RB, which is this vector here. Let me redraw it. There's my RB, there's my RA, and there is my R. Remember, the R is just that position vector essentially between the lines of action, guys. I'm going to repeat that. It is the position vector between the lines of action of the two forces in my couple. Whereas these position vectors are position vectors from the point O to the lines of action of the respective forces. Okay? So now, what have we got here? We've got RB equals RA plus R. RB, if we take RA plus R, we end up with RB. Okay? So what is R then? RA, if we just rearrange, we have RB minus RA. Okay, so it's important that we understand this bit of mathematics here, okay? So what is R? R is just RB minus RA, and where have we seen that before? We've seen that there. So if we substitute this in there, we see that our moment about O is actually equal to R cross F. R cross F. So the insight we need here, guys, is that all we need, when we have a couple, all we need is to determine a position vector between the two lines of action of the force. Because the moment about O and basically the moment about any point, okay, but the moment of these two forces about any single point will ultimately equal a position, will ultimately be equal to R cross F, where R is a position vector between the two lines of action. So when we have a couple, the moment of a couple becomes independent of the point that you're taking moments about. Because these position vectors, RB and RA, they in a sense, they fall away. It doesn't matter if we take moments about that point or that point or that point, because ultimately what we're going to have is R cross F, where R is simply a position vector between the two lines of action. And based on this, we can say that a couple moment, right, the moment of a couple is something called a free vector. A free vector, meaning it doesn't matter if you take moments of those two forces about any point on the body, or actually any point in the universe, we will end up with the same result. We will end up with the same result. If you take moments about any of a couple, right? You take the moment of that force about a point, and you add the moment of that force about the same point, that resultant moment will be exactly the same as if you take the moments of those forces about another point or another point. Because what happens is, all we end up needing and requiring are not these RAs and RBs. All we end up requiring is a position vector. This is in vector form. In vector form, it's a position vector between the two lines of action. In scalar form, it is a perpendicular distance between the two lines of action. I'm going to repeat that. When we're working with a couple moment, a moment of a couple moment, in three-dimensional space, when we often want to convert things into vector form, all we need is a position vector between the two lines of action. And in scalar form, all we need is the perpendicular distance between the two. Okay? So what you notice is then we get R cross F, and in scalar form we get F times D. Okay? So if that was F, and that's also F, that's just going in the opposite direction. The magnitude is equal to F times D, meaning what we have is, we have one of the forces times the perpendicular distance between the forces, right? We have one of the forces times the position vector between the two forces. Okay? Do you guys see the similarity between the vector and the scalar method? Okay? Let us do some examples. Okay, so I'm just trying to consider. We'll do some vector examples in the next video. I want to just quickly look at a couple of basic examples here. I'm not going to do the calculations, but I want to look at if we look at example 410, okay? So we've got this plate here, and we've got, let me get my trusty old pen pointer. So we've got this plate here. You can see it's resting against the wall with these two at these 2 points, and we've got a bunch of forces. Okay, but if you look carefully, you'll see we've got a F1 and an F1 and F1. These two forces form a couple, 200, 200, and they're separated by a perpendicular distance, 1.2. These two forces, right, form a couple, 450, 450, and they've got a perpendicular distance. And these two forces form a couple, 300, 300, and they have a perpendicular distance. Now, based on what we just learned, you could solve this in one of two ways. The first way is what we used to do before, is you choose a point, any point, B, A, wherever, and you take moments of all the forces about that point. Okay, and you get an answer. Or, and then you could take moments about that point, and you will get exactly the same answer. If you take moments about that point, of all the resultant moment of all the forces about that point, you'll get the same answer. Because when we're working with couples, they are free vectors, meaning they are independent of the point that you take moments about. But instead, guys, instead of doing that, instead of taking moments of all the forces about a point, the other way we can do it is we can use the scalar approach, which is we know what the magnitude of the force is. Let's just look at F1. That force 1 is going up. This F1 is going down. They have the same magnitude. It's a couple. They're separated by a perpendicular distance. It's a couple. So what we can do is we simply say the moment due to this force, the magnitude is F times D. Okay? So what they've got here is they said that anti-clockwise is positive. So if we take a look at this force here, that one's going up, that one's going down. What kind of rotation do you think that will cause? Well, a simple way to do it, if you don't understand, if you're struggling to know the type of rotation, is it clockwise, is it anti-clockwise? We know what the magnitude is, by the way. The magnitude is F times D. That's the magnitude. Okay? FD, where D is the perpendicular distance between the two forces. But why is there a minus there? Well, because this force causes a clockwise rotation. How do you see that? Well, imagine that there's a steering wheel here. Imagine there's a steering wheel. And you push up with your left hand and you push down with your right hand. What is the sense of rotation of that steering wheel? It will be clockwise. Okay? That's why there's a minus here. So whenever we're talking about couple moments, then imagine that there's a circular disc here, or a steering wheel, and you apply the one force on the one side and the other force on the other side, and then consider what type of rotation you have. So the magnitude, guys, the magnitude will be 200 times 1.2. Okay, that's what we get there. Okay, and then because it's going clockwise, we have a negative. What about this one? F2 and F2, 450, 450. What is the magnitude? It's simply 450 times D. F times D, which is 450 times 0.9. That's the magnitude. But then put a steering wheel here. And if you push that side and that side, what you're going to get? You're going to get anti-clockwise rotation. So that's why there's a positive there. And what about this one? Right? Well, this one, 300. What is the magnitude of this moment, couple moment? It's 300 times 1.5. That's what we get there. 300 times. And then what we see is there's a minus there because this will cause a clockwise rotation. And we end up with this answer here, which is clockwise. Okay? So, yeah, hopefully we're getting the picture there. And then just finally, don't want to make this too long, there's another example here. And what you see here is you see a force of 600 and 600. So we note, and they are parallel. Okay, they're opposite in direction. And it says determine the magnitude and direction of the couple moment acting on the gear. Determine the magnitude and direction of the couple moment acting on the gear. So 600, 600, and what we notice in this exercise is that it's actually quite difficult to determine the perpendicular distance. If you extend this line of action, extend that line of action, and you try to find the D, it might be a little bit difficult. So what they suggest, a solution is, let's just take moments like we did before. Let's take moments like we did before. Meaning, we just choose a point on the body and we take moments. So what they did is they chose this point there in the center of the gear, and they chose that point. And based on what we were discussing earlier, if we find we have a couple, right? Same magnitude, opposite in direction, separated by perpendicular distance. If I take moments of those forces about point O, and I take moments of those forces about that point there, what do you think the result will be? It will be identical, because the moment of a couple is a free vector. I can take moments about any point on the body, actually any point in the universe, as I mentioned before. We will get a free vector, because ultimately what will happen is, in the actual maths, the only thing that will matter will be that perpendicular distance between the two. So this is exactly what happens. They took moments about O, they got anti-clockwise 43,9, then they took moments about A, and they got also exactly the same result. Okay? So what are we meant to learn from this whole exercise? The one thing is that you can solve, if you've got a couple, you can solve it the traditional way by taking moments about any arbitrary point, okay? And so what we learned is we can take moments about any point if we've got a couple, because it'll give us the same result. But perhaps an easier way is if we can determine the perpendicular distances between these couple forces, so that we can then just calculate it using the scalar approach, which is F times D. That's the magnitude, and then we need to determine the direction. Okay? So I think that's good for now. The next couple of videos, I'll do some more examples, most likely vector examples. Thank you.